about compound interest and E. So compound interest is all about basically making money, I guess, in the bank. So let's start with an example. Actually, let me turn down the brightness on this. It's a little bit overexposed. There we go. So let's suppose that a bank claims that they have an account with a 12% annual interest rate. That sounds pretty straightforward, but it turns out there are actually a bunch of different ways that could happen. So the most obvious way that a bank account could have 12% annual interest would be just once per year. They look at how much money you have in the bank, and they increase that amount by 12%. So once per year, they increase by 12%. That's probably the most natural way of having a bank account with 12% interest, but it's not the only way. So here's another way you could do it. Instead of doing once per year, increase by 12%, what you could do instead is twice per year, so like every 6 months or something, you increase the amount in the account by 6%. In a certain sense, that's still 12% per year, but it's just kind of done differently. Or you could do it still differently. You could instead 3 times per year, you could increase by 4%. And again, because 3 times 4 is 12, in some sense, that's still 12% annual interest. What is interesting is that these different ways of distributing 12% annual interest actually produce different values. They give different things. So what we're going to do is we're going to write down a formula which allows you to find the value of an account regardless of how this is done, regardless of whether it's the first option or the second or something else. And then a little bit later we're going to talk about something called continuous compound interest and this mysterious number E. All right, so first of all, let's talk about the compound interest formula. You can derive this. It's basically an exponential function, but I don't know that it's necessarily worth the time and effort, so I'd rather just sort of write it down. Here's the compound interest formula. It's A is equal to P times 1 plus R over N raised to the NT. And I just want to make clear what each of these things, each of these numbers, or letters rather, represent. A basically is the new amount. It's the amount of money that you have in the account right now after time has passed. Usually that's what you're interested in finding. You're typically asked oh, you put this much money in the bank, there's this much interest, how much is in the bank after 10 years, and that would be what you're looking for in that situation. P is the beginning amount. It's the amount of money that you put in the bank at the very beginning. The reason why it's a P is it stands for principal, which just means beginning amount. All right, so what else do we have? We have N. N is the number of times per year that interest is compounded. So what do I mean by that? Well, in these 3 examples here, we were compounding interest at different times. Here, we were compounding interest once per year. In that circumstance, N would be 1. Here, in this second option, we were compounding interest twice per year. N would be 2. Here, we're compounding 3 times per year. N would be 3. So that's what N represents. T, not surprisingly, represents the amount of time that the account has been accumulating interest. And that just leaves R. So what is R? R is the annual interest rate written as a decimal. So, in this example, we had 12% annual interest, and so therefore R would be 12% written as a decimal, which would be 0.12. Okay, so this is the formula, and you can use this to answer questions like well, let's just do an example. So short, easy example. Let's say that you invest $100 in an account with, I don't know, 4% annual interest. And let's say that it is compounded monthly. Okay. The question is, how much money is there after 10 years? Okay, so it's as easy as just looking at this formula and identifying the correct values and then plugging them in. So A, of course, is the new amount. It's the amount of money that you have after time has passed. That's what we're looking for in this case, so that's going to be the unknown. So A is going to be left as a variable. P is the beginning amount, the so-called principal. That would be $100 in this case. 1 plus R is the percent annual interest rate written as a decimal. We've got 4% annual interest. So, written as a decimal, that's 0.04. N is the number of times per year you are compounding. Here we are compounding monthly, which means that we are compounding every month. In other words, 12 times per year. So N is 12. And then here we have N times T. That's the same N as before, so that's still 12 times T, which is time. How long has the account been in there? 10 years, so 10. And then all you have to do is just evaluate this expression. I'm not even going to go through the whole trouble of doing it because it's really something that you've seen millions of times. Well, not millions of times, but enough times. All I'll say about it is that when you're evaluating this expression, just be careful about the order of operations. Make sure that you simplify this expression in here first, that's parentheses, and then raise that expression to this exponent second, and then multiply by the 100 last. That's, PEMDAS, right? So just watch your order of operations. And a quick note, if you screw these problems up, like if you do the order of operations wrong, you tend to get really ridiculous answers. So like, if you worked this out and you found that after 10 years you had $500 trillion, that's probably wrong. So go back and check your work. So anyway, all right, so that's stuff that you've almost certainly seen before. Let's talk about something you probably haven't seen before. So this business about compounding interest with different frequencies, let's just talk about what the options could be. So there's sort of the standard option of compounding interest annually, which corresponds to once per year, so N is 1. Sometimes you'll see people talking about quarterly, so that means compounding 4 times per year, so N is 4. Sometimes you'll see monthly, that's what it was in the example we just did. That would be N equals 12. You could do it daily, like you could compound interest every single day, and that would be N equals 365. But why stop there? You could compound every single hour, which would be, I don't know what N would be. It would be, I guess, 365 times 24, whatever that is. You could compound every minute, which would be some gigantic number. I don't know what it would be. You could compound every second. You could compound every millisecond. And what is interesting is that it is true that each of these different options, each of these different compounding frequencies, whatever you want to call them, produce different results. What is interesting is that as you compound more and more frequently, annually, quarterly, monthly, daily, every second, every millisecond, the value of the account doesn't go to infinity or anything like that. It actually converges to a very specific thing. So if you do this more and more and more often, and you sort of, compound every millisecond, every tenth of a millisecond, every billionth of a millisecond, what you sort of reach in the limit is what is called continuous compound interest. And that is what that's the name that we give to a process where rather than compounding discretely, like every minute or every hour, instead we're sort of just compounding all the time. It's like the limiting terminal point of this more and more frequent compounding. What I want to say about it is the following. With continuous compound interest, where you're just sort of compounding all the time, there is actually a different formula. Okay, and here is the continuous compound interest formula. So basically, you know, if you're doing a compound interest problem and you see the word continuous, then you should be using this new formula, which is the following. It's A is equal to P times E to the RT. So A means the same thing as before in the previous formula. It's the new amount, usually what you want to know. P means the same thing as before. It's the old amount or the amount that you started with. T is the same thing. It's the time. R is the same thing. It is the annual interest rate written as a decimal. So none of that's changed. All of those letters mean the same thing. The only thing that's new is this peculiar number E. So what in the world is E? E is not a variable. It's not something that you, it's a constant. It is a special constant that gets used frequently enough that it has its own name, namely E. In fact, it's very similar to pi. Pi is a specific number. It's like 3.14 blah, blah, blah. But because that number gets used all the time, it has a special symbol, namely the pi symbol. Well, E is another such number. It's a number that gets used a lot. It's some special number. It's like 2.618 or something, I think. But it gets used so frequently that we have a special number for it. Let me just actually check to make sure that I know what it's 2.718, actually, 2.718. It's like pi. It's an irrational, decimal, like non-terminating, non-repeating, but 2.718 is good enough for most cases. So, so let's just, do a fast example with this. So let's say that, you have, $200 invested into some account, and let's say that it's 5% annual interest. Right, so you put $200 in, it's got a 5% annual interest rate. But let's say that it is compounded not monthly, not yearly, not quarterly, but continuously. Okay? And let's say find the value after 20 years. Okay? So, the only thing that changes is because you see this word continuously, you should be using this formula. But otherwise, everything's the same. So A is the new amount, that's our unknown. P is the old amount, the amount that you started with, that's 200. E is this special number, it's like 2.718. Raised to the R, which is, it's the percent annual interest rate written as a decimal, so that would be 0.05 times the length of time, which is 20 years, that's 20. And whatever that expression is, that's the value. Your calculator has an E button of some kind. It varies from calculator to calculator, but in order to compute this, you need to be looking for a button on your calculator that looks like this, e to the x. And I won't go into how to use it, basically because every calculator is different. But if you want to check it out and make sure that you're doing the right thing, I'll open up my calculator and just evaluate this expression here. So let's see. So this whole expression here, if you do it correctly, should give you, let's see, so e to the 0.05 times 20 times 200 should get like 543. 0.65. So if you get that number when evaluating this expression, you've done the correct thing. Okay, so that's kind of it for continuous compound interest. There's just one more thing that I want to talk about, which is this notion called effective annual yield. So let's talk about effective annual yield. So effective annual yield, which is abbreviated as EAY. So what is this thing? So here's the thing. As I mentioned, a bank can advertise a certain interest rate, like 12% or something, but there are a lot of different ways, as we've seen, of actually doling out 12% annual interest. You could do, as we saw, 12% all at once per year, or you could do 6% twice per year. In other words, you could compound interest once per year, or twice, or 12 times, or whatever. So the question is, if a bank advertises a certain interest rate, like 12%, how do you sort of compare the different compounding options? Like if you want to compare how much money you're going to get when you're compounding daily versus quarterly versus monthly, how do you sort of compare the effects of those different options for compounding? Effective annual yield is the way to compare them. Effective annual yield is really just, it's the percent increase, in a single year. So like the bank might advertise 12% annual interest, but if it's compounded, say quarterly, then the actual percentage increase that you get each year may not be 12%, but something else. And that's what the effective annual yield refers to. So in a certain sense, the effective annual yield is like the true percentage by which your account is going up every year. So let's just do an example. So let's go back to the 12% example. Let's say you have an account which is 12% annual interest, but let's say that it is compounded quarterly, in other words, 4 times per year. And let's say I want to find the effective annual yield. So what that means basically is 12% is what the bank advertises, okay? 12% annual interest, but the actual percentage increase that you're going to get is the effective annual yield, which is actually going to be different from 12%. All right, so let's go ahead and do it. So, you've got this formula, A equals P times 1 plus, of course, this isn't continuous compound interest, so we're going to use the regular compound interest formula. Here it is. So let's plug in what we know. We don't know the principal. It turns out to actually not matter in this case. R is the percent annual interest written as a decimal. That's 0.12 in this case. N is the number of times per year. Well, we're compounding quarterly, so that would be 4. And then here we have N times T, so that's 4 times T. We don't know how long. Now, what we want to know is what is the percentage increase at the end of the year? Like, by how much are you increasing this thing every year? This is similar to like the half-life problems and things that we've done previously. The way that this expression is written right now is telling you what happens 4 times per year. 4 times each year you multiply by this expression. I want to know what happens just every individual year. And to find that, I have to, as before, isolate the t. In other words, I have to rewrite this expression so that the exponent is a plain old t, not a 4t or anything else, but just plain old t. And it's the same process as before. I think I'll start by simplifying this thing right here. 0.12 over 4 is 0.03, so this whole thing is 1 plus 0.03, so it's 1.03 to the 4t. And now notice that I can rewrite this expression as p times 1.03 to the 4th to the power of t. That's sort of using the power of a power rule. Now, because the t is by itself, this version of the expression is telling you what you're doing every individual single year. So every year, which you multiply by, is this number right here, 1.03 to the 4th. So I'm going to use my calculator to see what that is. 1.03 raised to the 4th. I get something like 1.1255, okay, to the t. So here's the thing. Every year, I multiply by this number right here, by 1.255. Now, if you multiply by this number, what percentage are you increasing the amount by? You're actually increasing the amount in the account by 12.55. Right? So multiplying by 1.1255 increases the amount of money in the account by 12.55%. So that's what you're doing every year. And that is the effective annual yield. So basically, just to summarize, 12% is what the bank advertised. You know, it's what they put on their sign, 12% annual interest. But because the interest is compounded quarterly and not just all at once at the end of the year, the effective annual yield, the true percentage increase that you're getting at the end of the year, is not 12%, but actually 12.